Let's take a look at example 6. We want to find the antiderivative of sine squared 3x times cosine 3x dx. Looking at this function, the way that it's constructed, the integrand, it might be helpful to resort back to the simple notation for sine squared. When you see sine squared of 3x, that really means the sine of 3x, whole value squared. And by viewing it like this, we do see that we do have a composition here. It's the sine of 3x is being composed with the squaring function. And it looks like that's going to be a good substitution for us, because not only do we see that as being a composition, but we also see something that should be closely related to the derivative of that inside function, namely the cosine of 3x. So with that as our guide, let's let u be the thing under the power. Let u equal sine of 3x. Then when we calculate du, we have to use the chain rule here, be careful. Derivative of sine is cosine. Leave the inside alone. Times the derivative of the inside, derivative of 3x is 3. And then don't forget to differential, so you need your dx. We have du equals 3 cosine of 3x dx. This is a situation where we don't have exactly what's inside the integrand besides that, but we're only off by a constant. We can multiply it on the outside by 1 over 3, and that will allow us to multiply by 3 on the inside. And this will allow the substitution to work. We're going to have 1/3 the integral. This was my u, so this now becomes u to the second power. And the 3 cosine 3x dx, that part substitutes out for the du. So as was the goal under the substitution, we end up with an elementary antiderivative. Using the power rule, we add 1 to the power, divide by the new power. It's going to be u to the third over 3 times 1/3 plus c. This is equal to u to the third over 9 plus c. And then all we have to do is back substitute. Wherever we see a u, we can replace it with our original sine 3x. So the final answer is going to be the sine cubed of 3x all over 9 plus c. The next thing we're going to discuss is some guidelines for making a change of variables. So a lot of times you might have an integrand where there's competing ideas as to what you might want to try in terms of a substitution. So to choose a substitution u equals to g of x, it's usually best to choose the inner part of a composite function, such as a quantity raised to a power. If we have like a radical, like a square root or a cube root, try letting u be the thing inside of that radical. If you had, let's say, like a power function, like a e to some function, or like 2 to a function, whatever, let u be the exponent of that function. Once we've done that, you then want to calculate the derivative with respect to u in differential notation. Du would be equal to g prime of x dx. From there, we're going to rewrite the integral in terms of the variable u, find the resulting integral in terms of u, and then don't forget the last step should always be to back substitute to obtain the original antiderivative as a function of x. Theorem 5.14 is kind of a generalization of the power rule, something we've seen a bunch of times up to this point. But again, if you have, let's say, a function is being raised to a power, and if you also have the derivative of that function as part of the integrand, then we can do the substitution, let u equals to the thing under the power, and under that substitution, this would reduce to just simply u to the nth power, which we can apply our basic power rule for integration. Let's take a look at a few examples. In example 7, we are asked to do substitution in the general power rule. As long as you're comfortable with u substitution, there's really no reason to think of this as anything new or anything different. It's still following the same guidelines we had from before. If I look at example 7 part A, we see that we have a function that's being raised to the 4th power. So let's let u be the thing under that exponent. Let u equal 3x minus 1. Then our du will be equal to 3 dx, which is perfect because that's exactly what else remains inside that integrand. Under this substitution, we're going to get the antiderivative. I'm going to focus on the substitution part first. It's going to be u to the 4th. So I swap this out for u. It becomes u to the 4th. And then in place of my 3 dx is equal to du. From here, it's a basic antiderivative of a power of u. We add 1 to the power, divide by the new power. Don't forget your constant of integration plus c. And then last up, back substitute. 3x minus 1 to the 5th, divided by 5, plus c. Again, one of the beautiful things about finding antiderivatives is if you want to check your answer, if you simply do the derivative of what we found, it should match up with what was inside of the original integrand. Let's take a look at part B. This one's a little more subtle, where we have a product of two things. It's the product of e to the x plus 1 times e to the x plus x. So we look at it and we say, there's not necessarily like an inside thing to do. You could expand it and integrate most of it, but there'd be one term that up to this point we'd be stuck with. But this one will actually work as a substitution. And the thing that's going to want to guide your substitution is, again, look for, in this case, a part of the integrand whose derivative is also present. And if I would let u be this piece right here, let u be e to the x plus x. My motivation for doing that is that the derivative of that part, derivative of e to the x is e to the x, derivative of x is 1, and then that whole quantity would be multiplied by dx. That's the remaining piece of what's there. So under the substitution, we're going to get the following. This is going to become, this piece is simply u, and this whole other remaining part, e to the x plus 1, quantity times dx, that simply gives us du. We can integrate this. We know this integrates to u squared over 2 plus c, and then we can go ahead and substitute. E to the x plus x squared over 2 plus c. One of the things that I always warn students, especially when we're doing these types of problems on the board in class, is, or in any calculus course, is that typically students will sit in a lecture hall or online as you all are now, and you'll see, professors go through, u sub problem by u sub problem. And for the most part, every single time we're always making the correct, u substitution. Let u be this expression, and then it seemingly works out because we know what to do ahead of time because we've done a million of these. One of the things that I will caution is you might try a particular u substitution, based upon things we talked about and suggestions and tips that I've given you. And they might seem like great ideas at the time, but not every substitution that we make is always going to work. If that's the case, don't be squeamish. Try and take a particular u substitution as far as you can get in terms of being able to get a new integral in terms of the variable u in our case, and then seeing if you can integrate that thing as far as you can take it. But not every u substitution will work. And if that happens, don't be afraid to go back to the drawing board and try something different. For example, I could have tried to maybe let u be the other piece. If I try to let u be e to the x plus 1, then I can try to work it through. Our du would be e to the x dx, but that wouldn't allow me to fit and totally substitute out to get a antiderivative in the variable u. So, just be on the lookout that while we try to give you a lot of good suggestions in terms of what to let your u substitution be, not every u sub will work. If the particular one you tried isn't happening for you, don't be afraid to go back to the drawing board and try something else.